welcome to another edition of Coonrod's Corner, brought to you by the Rogers Corporation. Today's topic, RF influence due to whole wall roughness of plated through holes for 5G and other applications. Now here's your host, John Coonrod.
Hello, welcome to Coonrod's Corner. My name is John Coonrod. I am a technical marketing manager for Rogers Corporation. Today I'm going to be talking about RF influences due to whole wall roughness of plated through hole technology, and specifically I'm looking at applications in the frequency range for 5G and millimeter wave. Now over the years there's been a lot of enabling technology that has given us applications of much higher frequencies. So some of these chipsets that are now operational and very functional at millimeter wave frequencies has created a lot of applications at much higher frequencies than what traditional printed circuit boards have been used in the past. And because of that, we're actually having to rethink some of the structures that we thought was pretty well understood for printed circuit boards, and now at higher frequencies they could have a different influence. And one of them is plated through holes and plated through hole roughness. The two pictures that are shown here are from the plated through hole study that we did to look at whole wall roughness. The picture on the upper left is using the RO3003 G2 materials, which is a newly released material that has been optimized for 77 gigahertz automotive radar. And then the bottom left picture is the RO4730 G3 materials, which is actually used in a lot of 5G applications. And you can see by the higher magnification views of these plated through hole walls that one has a much rougher through hole wall roughness than the other. So the RO3003 G2 you can see has a very smooth through hole wall roughness, or it is very smooth. And then the circuit that's based on the 4730 G3, you can see the whole wall roughness is much rougher. In the study where we looked at whole wall roughness, we actually looked at several different test vehicles that would be appropriate for this kind of a study. And what we decided to do was use a microstrip transmission line with a via that would transition the signal from one copper layer to the other. The reason a microstrip transmission line for the test vehicle is because it's less influenced by the variables of making the circuit in the printed circuit board fabrication process. Now let's go ahead and take a look at the test vehicle, and I'll explain a little more detail. Shown here are two different circuits, and on the left is the standard microstrip transmission line, and that's just really as a reference. And as you can see on the top copper layer, it's just really a signal conductor from left to right, and the bottom is just a large copper plane. Now in the area where the connectors are applied, the left and the right side of it, there is a slightly different structure. That's a grounded coplanar waveguide structure just in the area where the pin of the connector touches the circuit. And then away from there, it becomes, in the body of the circuit, a true microstrip transmission line circuit. Now to the right is the test vehicle that we actually used in this study, and it is technically a loosely coupled grounded coplanar waveguide transmission line, but it's so loosely coupled that it really is MSL, and that means microstrip-like, so it really behaves electrically like a microstrip line, but you do have some benefit from the light coupling of the grounded coplanar waveguide for getting better return loss at much higher frequencies. And the minimum frequencies that we were shooting for valid information in the study was 40 gigahertz, and we were able to achieve that. The other benefit to this kind of configuration is around the via transition that's right in the middle of the circuit. That is also grounded coplanar waveguide with tight spacing to the neighboring grounds, and that allows us to really optimize the transition for the via. And that was able to be done and get very good return loss up to beyond 40 gigahertz on all the circuits that we tested in this study. In this study, we took several precautions to make sure there was minimal material variations, and one of them was when evaluating circuits on these two different materials is we started off with a large panel, 24 by 18, and then we cut that panel in half. And half the panels had circuits made, and the other half of the panels also had circuits made. And the idea was we were going to compare a lot of circuits on each panel to look at circuit-to-circuit variation, and then we were looking at the same material, obviously, but looking at panel-to-panel. And the panel-to-panel variation is typically an influence due to the circuit fabrication. The material itself is very well controlled for dielectric constant being consistent across one sheet. And in this case, we use one large sheet, cut it in half, and then have the circuits processed in two different panels that way. So we did that for both materials, the RO3003 G2 materials and also the 4730 G3 materials. The information shown here in the tables is from the study that we conducted looking at plated through hole wall roughness. And to begin with, the data under the heading with the orange color is the raw phase angle measurements that we took. This is unwrapped phase angle measurements and at the three different frequencies listed, 24, 28, and 39 gigahertz. And then to the right of that, the columns that have the yellow header, that's actually differences of the circuit. So in the circuit ID, I'm showing P1C1, that means panel 1, circuit 1, and then I go P1C2, P1C3, on and on. And really, I'm using P1C1 as the reference, and then I'm comparing these other circuits to how they behaved on the same panel to that circuit. And that's the information under the yellow headings. And then to the right of that, I've given some basic statistics on the differences. And that, again, is at 24, 28, and 39 gigahertz, and I'm showing average differences and also standard deviation and range. And I did that on 2 panels, obviously, and this again is for the material RO3003G2 materials, which has very smooth whole wall roughness. Now for a little more information on the test vehicles and the materials used in the study. To begin with, all the circuits were built at the same time and using the exact same tooling. So we used the same artwork, the same drill files, the same everything. And we were able to do that because both of these materials have the same nominal dielectric constant of about 3.0. Also, we used the same thickness of materials. They were all 20 mils thick. And also the copper types that were used were not the same copper type, but actually very similar for copper surface roughness. Both of them have, on average, a copper surface roughness of about 0.8 microns RMS. And we know that copper surface roughness does impact circuit performance. So having everything the same copper roughness, same thickness, same decay, that allows us to build all the circuits with the same tooling and all at the exact same time. So we did that, and we also alerted the PCB fabricator to make sure that they had optimized drilling conditions for these materials, and basically they babysat these panels running through their process and really did try to optimize the processing as best they could. Now, also along with the study, we looked at a repeatability study, and essentially what we were doing was assembling a circuit, one circuit only, testing it and disassemble it, and then retest again and again and again, multiple times with 2 different operators, and also over different days, different environments, and actually different calibrations. And we did that to see how repeatable the results were. And what we found was for the particular testing that we're doing with phase angle, and specifically at 39 gigahertz, we had a repeatability about 1.2 degrees at 39 gigahertz. And also, of course, that means a range of about 2.4 degrees. So the accuracy of this measurement is around plus or minus 1.2 degrees at 39 gigahertz. The table of information shown here on the left are the summary, basically the statistics summary for the circuits that we're using the RO3003G2 materials, which has the very smooth whole wall roughness, and the tables of information on the right. That is from the circuits being tested using the RO4730G3 materials with the rough through whole wall roughness. Now on the left, the RO3003G2 materials, you can see that the average standard deviation in the range for panel 1 is slightly different than panel 2, and we did that purposely. So we did all the comparisons for circuits within one panel only, but we did not try to compare circuits on panel 1 to panel 2. The reason we're actually showing that data is showing the potential difference in processing and making circuits from one panel to another, because there is normal panel variation from panel to panel, and circuits being processed different on one panel than the other. Even though we really did babysit these and try to make sure as making the circuits they were optimized, there are still very small differences in etching, making the circuit, copper plating thicknesses, trapezoidal effect, there's several things. But in general, if you look at the numbers here and consider the accuracy of the measurement, the repeatability of plus or minus 1.2 degrees and a range of 2.4 degrees, basically that number is telling you what the noise floor is. Then considering these numbers and also the influences of making circuits, this basically tells you there really is no RF difference between circuits with a smooth whole wall roughness compared to circuits with vias with a rough whole wall roughness. This now concludes this episode of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.